Oh, really quickly, hold on. I this one? I missed it. There was for the locker decorating at lunch, come out to some patios.
And then this one?
Yes. There's going to be Christmas music, and it's going to be easy. The student council worked really hard to have them in the shape of your lockers, so all you're going to do is tape it up. Done. Yeah.
What is baby fish used to?
Before Christmas break, I think, right?
What?
Oh, I don't know. They just said you can start turning them in. Go with Mrs. Cameron or someone in your book. On HCTV, probably. Anyway. So, paragraph number 29. Sorry, someone texting again. Alright. Paragraph number 29. Let f and g be functions that are differentiable on the open interval a to b containing c except possibly at c itself. What? It's okay. If the original limit produces an indeterminate form, then. Long story short, there could be possibly a hole at c. We know with limits. It's coming. The final's coming, right? Limits will be on it. Messy. Don't we know? Even if there might be a hole at c. Even if there might be a hole. Question, does the limit exist? Yes, and the limit will equal, it just depends on, we'll just call him y1. Okay, whatever. y1. The limit does exist. When does the limit not exist? When the two-sided limits do not agree, or if it's some sort of infinite, I guess it would technically not exist, but as long as they're agreeing, don't we still answer? What would this one be as you come towards C? Positive infinity or negative infinity or DNE, because they do not agree, right? But long story short, this whole except possibly at C is just saying, hey, there could be a hole, no big deal. There might be a discontinuity, but as long as it's differentiable everywhere else. I haven't seen, I don't think I've ever given a problem where this condition is not true. However, it's still good to put in the rule. If the original limit produces an indeterminate form, I need you guys to underline indeterminate forms. In homework, there's a section that says something to the effect of, can L'Hopital's rule be used? Or there could be a problem where it just says, hey, solve using L'Hopital's if necessary. The only time we can use L'Hopital's is when the limit produces an indeterminate form. Well, what are the indeterminate forms? Uh-oh, they're on the forever card too, because 0 over 0, that's one. We already know that one. Keep going. Infinity over infinity. We kind of already know that one because we've faced it with horizontal asymptotes and with infinite limits. We've faced it before, but we had degree tests to help us, which are probably still the easiest way to solve those. But you could use L'Hopital's as well. But we also have these new ones, infinity minus infinity. Which one's greater? I don't know, so I don't know the answer. 0 times infinity. That one's a little trickier to explain, but it's also indeterminate. 0 to the 0, 1 to the infinity, infinity to the 0. All of these are indeterminate. The main two are the first two, but other ones may appear and we have to know how to deal with them. Question, why couldn't we use the old way on this one yesterday? We were doing the old way, right? We were going, we were stuck. Why? Couldn't factor, I mean you could, but it didn't cross out. Can't rationalize because there's no square root. There's a square root one in your homework. Yes, I want you to do it the old way and then couldn't rationalize, couldn't multiply by the conjugate and have it fix anything. You would have, in the olden days, in chapter 1, gone to your calculator. Well, that's lame. We're not going to our calculator. There's no calculus. There's bound to be a better way. And we said, yes, there is, and it will be L'Hopital's. Question. What did I do to get to 2? Ooh, that rhymed. Katrina. Yeah, I have a question. You have a I can't make it go higher, but I can get all of my notes and drag them down. But now, L'Hopital's rule. There you go. Oh. So not make the board go higher, make the notes go. Is that better? How did I get to 2?
Okay.
Pause. First, I plugged in. I didn't do anything else first. Because we have to make sure we have an indeterminate form. If I asked for L'Hopital's rule on the forever final on Thursday, I'm going to expect you to say something about f and g are differentiable. The original limit ends up being indeterminate, and then I can use my rule. So first I plugged in, and when I plugged in, I got 0 over 0, and we're like, sweet, keep going. But there's no algebraic way, so instead we said, whew, now we know derivatives, we can use L'Hopital's. What did I do to, after plugging in and figuring out indeterminate, what did I do to keep going, to go to the next one? To the derivative of quotient rule. No. L'Hopital's is much nicer than that. That's what you're like I said. Question. What did I do?
You just take the derivative.
Derivative of the top, derivative of the bottom. Is this how I normally take derivatives of quotients? No, but this is not quotient rule. I'm not taking the derivative. I'm using L'Hopital's, which says, sweet, application, derive the top, derive the bottom. E to the u times u prime minus 0 all over 1. Then how did I get to 2? Plug it in, and it was great, and it was good, and it was ready to go. So this is the new way. Let's go see if the new way works instead of the old. How many of you guys didn't like the whole rationalizing multiplying by conjugate, simplifying complex fractions, having to factor and cancel? Let's see if there's another way. After you get 0 over 0 with L'Hopital's, you can say, sweet, indeterminate. So we can solve by going the limit as x approaches -1. Are you still rewriting the limit? Yes. Struggle. Derive the top, 4x. Derive the bottom, 1. Plug it in, -4. Dun, 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 dun.
Yeah.
Woo! Look at that. Isn't that nice? Because we didn't know derivatives first, and we can't learn derivatives until... Anyway, that's what all the BC kids... Remember, you went to go solve limits, and I just used L'Hopital's. Anyway, now you know. Was that not? Anyway. Or Jared Wire. What do I do? It's indeterminate! Now, you could still use degree tests, and it might still be the easiest way, but technically, question, what would you do if you plugged in? Nope, L'Hopital's, if you took the derivative. 6x over 4x. Well, ew, I can't do... What can you do with x's? If you plug in infinity, it'd be 6 infinity over 4 infinity. Maybe you would still figure it out, but what's 6 over 4? 3 over 2. Now, kiddos. What? It's good stuff? Or is it about something else? Either way. The whole IND thing, independent, indeterminate, what does that even mean? Okay, that's one way of showing it, but we're actually going to show something a little different, okay? We did keep going with the algebraic, and it's still great for you to recognize, ooh, I'm not done, I don't know the answer, I have to keep going, except now, as soon as we see an indeterminate, we're going to do L'Hopital's. We're going to say, sweet, derive the top, derive the bottom. So, to make it a little bit clearer, we're doing L'Hopital's. IND is good, it is indeterminate, but it's not as good of an abbreviation. And it doesn't necessarily lead you directly to where you're supposed to go unless you know your forever card really well to say indeterminate L'Hopital's. Let's go. Now we have another one. 0 over 0. L'Hopital's. What do we do? Good. 2e to the 2x all over e to the x. Well, wait a minute. Don't do L'Hopital's again. Don't take the derivative again. Don't even cancel out. What happens when you plug it in? Anything to the 0 is 1. 1 times 2 is 2. Anything to the 0 is, it works! 2. Dun, 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 dun. We already figured out that one works, yeah? Do we like L'Hopital's?
Yeah.
Maybe. Let's keep going. That's forever number 29. Let's see what we do or should do with this one. Old-fashioned way. Yeah, no. We're not. But, before we can do L'Hopital's, what do we still have to see? What do we still have to try? Hey, it's a limit. Who cares? I know it's in this section, but still, any limit you try to plug in. 0 minus what sign of 0? 0. Sign starts at the center at 0, 0. All over 0. We could say keep going, but that means simplifying complex fractions, multiplying by the conjugate, factoring. No, there's a sign. Ew, gross. L'Hopital's. Take a second. Find me a derivative. Find derivative top. Find derivative bottom. Plug in. Let's see how it goes. Did you rewrite the limit? Ooh. If you didn't rewrite the limit, you put it in there right now. If you didn't rewrite the limit, you put it in there right now. Statistically, those that don't put the limit each step of the problem are going to forget the point. What you guys get as the derivative of the top? Nice. All over?
Yeah.
What happens when we plug in?
Wait, but if it's 0 over 0, guess what we can still do?
You can already
Look at that.
1 minus
You don't want a factor, there's still a cosine. We're gross. So just go again. Okay. Derivative of 1, 0 minus cosine x. Positive sine of x all over. Where's Charlie? There's no being performance. 6x. Plug it in. Oh no! It's 0 over 0! It's okay. Keep going. But look at that. Equals. Limit as x goes to 0 of cosine x all over 6. Did you see it?
Yeah.
Took us a little while. We needed the x cubed to go ahead and break it down all the way, but it's alright. We got there. Now we can plug it in. Cosine of 0 is 1, and 6 is 6. Done. And if we had done that one at a table, we would have gotten something weird like 0.1665 something. Most of you don't know the fraction 1 to 6. So this was actually easier than even the calculator. And takes less time. You just have to know how to take the derivative of the top, derivative of the bottom, try to plug in, and if you need to, go again. And again. How about this one? Wait a second. I want you to plug it in. Let's see what conclusion you get. So I'm going to give you tons of time on it, because I know you're still learning. Some of you might not have realized. Did you get 1 over 0 minus 1 over 0?
Yes.
Do you remember what 1 over 0, what form that is?
No.
It's not indeterminate, it's infinite. Vertical asymptote, 0 on the bottom, the bottom on the top. It's infinite. Well, what kind of infinite? Well, we would have had to try to plug in, but long story short, you could kind of think about it as maybe infinity over infinity? Sorry, not infinity over infinity. Infinity minus infinity? Sort of, kind of. If it's infinity minus infinity, well, that's indeterminate. Right? So let's see what happens with L'Hopital's. Some of you might be thinking about the whole, like, wait a minute, but don't we have to come from both sides of 0 to figure out what type of infinity? Yeah, I didn't go into all the craziness of which kind of infinity it is, positive or negative. If you think about it, they're actually both kind of D and E. The sign's going to go to negative from the left and positive from the right. 1 over x is going to go to negative from the left and positive from the right. Oh, stinkity. Good question. Can you use L'Hopital's?
No. You can simplify it.
What is L'Hopital's? Here's where it starts to get a little confusing because L'Hopital's actually only applies to 2 of the indeterminate forms directly. L'Hopital says the limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of x over g prime of x, as long as f and g differentiable functions on an interval containing C, but maybe not at C itself. Do we have just an F over a G? Uh-oh. So maybe before we can even do L'Hopital's, we need to get a common denominator. We need it in the form F over G. So L'Hopital's is cool, and it's really good, especially when you have an F over a G, you can just go. And it doesn't work just plugging in. But if you don't have an F over G, you gotta get an F over G, which means, let's see if you guys can track. What would you multiply this one by?
X over
We need him, so we can say X over X sine of X. What would we multiply this guy by? Sine of X over sine of X. Maybe before we can really make any determination, maybe we need to make it look like an F over G. Now do we have an F over G? Yeah. Okay, now hold on. Now that we have an F over G, try plugging in now. Now what do you get? 0 minus 0 over
0.
So is it truly L'Hopital's? Yes. Did we technically know from here? No. Why? If we were to go and test signs, this actually would be the limits do not exist because the one-sided limits do not agree. The limit does not exist because the one-sided limits do not agree. But when we put it together, we're like, oh, snap. Maybe the limit does exist. I need who or what? L'Hopital's. But we just weren't ready to do L'Hopital's until we could get it in an F over a G. Okay, so L'Hopital's. Derive the top, derive the bottom, and as you do, Katrina, go. I know, but remember, we wouldn't have gotten it right without a calculator from the beginning, because we would have said DNE minus DNE is DNE. Maybe that's another kind of awkward indeterminate form that we just don't exactly know. Or isn't explicitly stated. But 0 over 0, we know that's what it is. So as you guys are going, I'm going to try and catch up. 1 minus cosine of x, yeah? All over. Okay. Second D first. Oh, don't be scared. Sine x times 1 plus product rule is a plus, quotient rule is a minus. First D second. Well, still, what are you trying to do? Plug it in, plug it in. 1 minus 1 over 0 plus 1 times, no. Sine of 0 is 0. X is 0. 0 times 1, aw, stink, guys, what did we get? Maybe try one more time. Ready, set, go. L'Hopital's. See if it's a lost cause, or maybe if something works out.
Could you not cancel out the cosine?
No. Reason being, remember, with fractions, they have to match. Does that make sense? The entire factor has to. If we could have maybe like pulled something out and gotten 1 minus cosine, then we could have factored it in. Good question. When as x goes to 0 of, do you guys get sine of x on top? All over? Okay. It's hard, but you can do it. Derivative of sine is cosine. Derivative of x cosine x, what we gotta do? Second D first is another cosine. Plus first D second is x times negative sine of x. Which would be, I'm just going to rewrite and make plugging in easier. Two cosine x minus x sine x. Aw, stink, what happens when you plug it in? Trying to trick you and have you guys just say 0 over 0, but you're smarter than that, right? You have to do it for yourselves. 2 times cosine. Sorry, that's a cosine. My marker's being funny because my board's dirty. Cosine of 0 is 1. 2 times 1 is 2. 2 minus 0. Oh my goodness. 0 over 2 is Got an answer. 0. Got an answer. 0. Does that make sense? Okay. Was it a little rough? But we didn't have to use a calculator to get it. Ooh. Give you a second to write it down. Let's talk about whether or not we need a local test, and then how to apply local test. Let's talk about whether or not we need L'Hopital's, and then let's talk about how to apply L'Hopital's. Try to plug in. Plug in what? Infinity. Try to plug in. Plug in what? Plug in infinity. Try to plug in. Plug in what? Infinity. Okay. We're doing fuzzy math. But technically, we're doing fuzzy math, so let's see if we can figure out what's going on. Put little quotes around it. Remember when we were plugging infinities before? Can we make any conclusions? Do we know anything about 1 over infinity? Yes, bottom wins. What is it?
Approaches 0.
This approaches 0. Bottom wins. 1/10, 100, 1,000, 1,000,000, right? That's 1 to 0. So 1 plus 0 is 0. If you didn't know L'Hopital's, and even if you knew calculus pretty good and knew that was 0, pretty well, I should say. I apologize, like Americans. But coming back, wouldn't most of us say, yay, it's 1? No. And we're wrong. It is not 1. Because who is this? It's indeterminate. The question, is it in the form that we need to do L'Hopital's? No. Okay, so we need to get a fraction. An f over g. Oh, okay. So hold on, we just need to rewrite it first. Alright. So limit, as x approaches infinity, of, what will we multiply top and bottom by? X over x. Wouldn't we get x plus 1 over x? Okay. X over x, x plus 1 over x. Uh-oh. Now we have infinity over infinity to the infinity. Does that help any? No. Do we just have an f over a g, or do we have somebody else? This one's a little special. It's going to take us a little while, but the conclusion is going to be pretty interesting. I want you guys to set this whole thing equal to y. We know we need L'Hopital's. 1 to the infinity is not 1. It's indeterminate. We're not sure who he is or what he is, so we have no way of making a conclusion without our calculator unless we can get this to look in or like the form f over g. Well, there's a to the x in the way. We've seen that before. When has there been a to the x in the way before? No. Woo! What are we going to do? Right, no we're not. We are going to put an ln on either side. Now it's weird. I had to make y equals in order to be able to put an ln I can't do that, on either side. And there is a property of limits that actually allows us to
Do that.
This is from a long time ago. We can bring the ln in. I keep saying whatever. The natural law. We can bring him inside. Why would we do that? Because once he's inside, I can bring the x down. Once he's inside, I can bring the x down. Limits say that you can bring functions, like basically you can take limit of f of g is the same thing as f of the limit of g. Anyway, there's this whole property. We wrote it down a long time ago. No, I think it was just like a properties of limits, just to be like, hey, you can do this stuff as you're plugging in. We didn't really use it before that. Not really. We can bring the ln in. We can bring the x down. Oh no. What do we still need this to look like? A quotient. When you say quotient, don't say quotient. We want it to look like a quotient. How do we make it look like a... We keep the ln. I know, it's okay. You can read for a second. We keep the ln. And we keep him, but we don't want times. We want divided by. And if it's multiplying by this, what would it be divided by? Now, usually we go from division to multiplying, from dividing to multiplying by the reciprocal. But if we need to go back, what are we going to do with it? We're going to flip it. Dividing by a function is multiplying by the reciprocal. So multiplying by a reciprocal, we have to flip it to go back to division. Now I know that this is nasty. It's a little bit counterintuitive, but basically we're undoing a multiplication and putting it back like a division. Why? This is the way that we can say, look, it's an f over a g. It's not pretty, but it's an f over a g. And if we were to plug in ln of infinity plus, what would be infinity over infinity? I don't know, except the degrees are tied. What would that be? 1, ratio of leading coefficients. What's ln of 1? What's 1 over infinity? Woo! Finally! L'Hôpital's, now we're ready. Took us a while. But L'Hôpital's, now we're ready. Ryan.
Would it make sense to use the log properties and make it ln of x plus 1 minus ln of x?
You could. Why?
So it'd be easy.
Ryan's like, wait a minute, we have to take a derivative of this gross quotient. So he's like, hey, wait, before we do L'Hôpital's, why don't we go ahead and rewrite, which is an excellent idea, and say quotient property says you can take ln of the top minus ln of the bottom when you have a quotient. It's still going to get 0 over 0. We're still going to use L'Hôpital's, but our derivative just got a whole lot easier. Okay. Derivative of the top, derivative of the bottom. ln of x plus 1. 1 over u. 1 over x plus 1 times u. But what's the derivative of x plus 1? 1. Minus ln of x. 1 over x. All over u. What's the derivative of 1 over x? Rewrite. X to the negative 1. Bring down the negative 1. Make it a negative 2. Negative 1 over x squared. Ew, this doesn't look any better. But wait, maybe we could simplify? What would happen if we simplify? We have multiple options. We could try to multiply by x times x plus 1 on top and bottom. Or we could just try to get rid of this yucky x squared. What do you guys want? Okay, let's get rid of the x squared. So let's just multiply top and bottom. Can I do a negative x squared to get rid of the whole thing? Then we have ln of y is chilling. Ln of y is chilling. The limit as x goes to infinity of, bring in the negative x squared. Fine. Bring in the negative x squared. Oh, that's positive x. All over, that all goes away. The negative turns into a positive. Mistake. Now what? Maybe common denominator? Because the limits to infinity, don't you want to do degree test? So we can do times x plus 1 over x plus 1. Then we end up with the limit as x goes to infinity of, now they have common denominators. So we're going to have negative x squared plus x squared. Well, that goes away. Then we're going to have a positive x over an x plus 1. Oh, is this getting us anywhere? Infinity over infinity, we don't know, but wait a minute. Hold on. Ratio of leading coefficients is 1, or you could do L'Hopital's one more time. Derivative would be 1 over 1, which is 1. Oh my goodness. The limit is 1. No. What? Oh. This limit is 1. But what was I trying to solve for in the very beginning? Which limit? This one. And who was that one? Y. So what am I going to solve for down here? Y. How do I get rid of Y? Y, which equals my original limit as x goes to infinity of 1 plus 1 over x to the x is e. Dun, 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 dun. Now, we could have to do that every time we see this, which isn't often. Or we can memorize it. So that the AP tries to trick us, we don't have to do anything. What do you guys think? You sure you don't want to do that every time? That looks fun though. So let's go ahead and write ourselves just one quick forever card. It's okay. But hold on, wait a minute. Didn't we have a special limits card? What forever card was that? Didn't we have a special limits card? Now we could use an entire forever card on this one formula, but I'm not feeling it. You guys feeling it? Yes. You are? Okay, if you're feeling it, magically make another card in your cards because we're already kind of going to run out. So, I mean, not totally, but maybe possibly. So anyway, where am I going right now? To the forever cards. They're online, true. What are we missing right now? I think L'Hopital's we haven't gotten yet. Why don't you guys take a second and while I pull up the forever cards, write down another example. He's not as hard as the last one. Ooh, I'm going to die. I promise. However, he does require a similar procedure. See if you can figure out how to make him f over g. Hint, you have to change the multiplication to division. Ooh, we just did that. But how? Come on, computer.
Yeah.
Does one of them look kind of familiar?
Yes.
It looks kind of familiar, a little bit different. Rashia, throw in a number 4. Maybe I know a little awkward. Right? Throw in a number 4. Oh, there we go. The limit as x goes to infinity of 1 plus. Hold on, think about this for a second. I think it's n over x. Let's not do n. Let's do So in the one that we just saw, it was 1 plus what over x? 1 over x. So 1 plus 1 over x to the x is e to the 1. 1 plus 2 over x to the x is e to the 2. 1 plus 3 over x to the x is e to the 3. This is one variation. But to be honest, I haven't seen this one near as much as this one. Now, coming back to this example. If you plug in, you get 0 times, technically, infinity. That's no good. 0 times infinity. That's no good. But You need to get it into an F over G. I'm trying to give you one last tricky. What could come up that's weird in homework? Why did I do this? And if I plug in now, 1 over 0 is infinity, ln is infinity, I end up with infinity over infinity, and what can I do with that? L'Hopital's pedal. Anyway, what are you going to do? Derive the top, derive the bottom. Quotient rule? No! How are you going to rewrite it? X to the -1/2. Get out of here, cool kids.
They're like testing out.
Tomorrow we're going to go ahead and grade 3-7 and 7-7 and see which ones you have questions on. No quiz on this, it'll just be on the final. Bye, cool kids. See you later. Study those forevers. What happened to that?